So it's my pleasure to introduce your first speaker, Mitch Goldberg from NOAA NESDIS, Chief Scientist.
Thank you.
He have long resumes and then get working in NOAA for a long time and NESDIS different division, meteorology and collaborating with NASA. He's a fellow AMS, I want to emphasize, and then I've been affiliated since my graduate student time, AMS. He have a PhD from University of Maryland and have a most distinguished alumni award from the department. So welcome, Mitch.
Thank you. Thank you. I think I'm the first and last speaker, right?
You are the first and
last speaker. So thank you for inviting me, number one. I think the presentation is probably 40, 45 minutes, so pace yourself. And I am a meteorologist, not an oceanographer, but I'm learning a lot. I had a lot of help on this presentation by Paul DiGiacomo, who's the division chief of the Satellite Oceanography and Climatology Division with the NESDIS, and Veronica Lance, who's also a NESDIS, and Ross Parson, who's with NCI. He's the deputy chief of the Oceanographic and Geophysical Science and Services Division in NCI. So I think everyone understands climate change and the impacts that we're seeing, sea level rise, more coastal flooding, more extreme weather events, increase in ocean heat content, salinity, changing fish habitats, more harmful algal blooms, more severity, and more beach closings and things like that. So we're seeing it, right? It's not going away. And so what we're doing within NOAA is that we want to make sure we provide the right information to communities so we can mitigate the impact for climate change. Because even if we reduce greenhouse gas emissions, which is really important, this impact is going to be with us for a while. So it's really important that we focus on that. And what I'm going to do is I'm going to talk about the big picture, what we're doing at NOAA, so you understand what we're doing at NOAA. Then I'm going to drill down into what we're doing at NESDIS with respect to satellites, and then also with NCI. Then I'll talk about next generation satellites with the geostationary satellites that we're planning. And that's the collaboration with NASA will be that part, because they're our major partner in developing our satellites. There's other collaboration with NASA in the sciences, but I won't really touch on that too much and focus on what NOAA is doing. So NOAA has a new strategic plan that focuses on climate. And so in the first part, we're trying to establish NOAA as the primary authoritative source for climate, just like we do for weather. If there's a hurricane, right, where do you go to? You don't go to EPA, you go to NOAA. You go for NOAA to the Hurricane Center. And so we want to be that same source for climate. We want to work in terms of environmental stewardship, economic development, in the sense of providing that information so our economy is resilient to climate change. From current, providing information on current conditions, but also projections way out into the future, so one can plan. Do we build more seawalls and things like that? What do we do? How will species, fish habitats change over the next 20, 30 years? That's really important for the blue economy. And of course, equity is really important. Equity, making sure that we're providing services to all communities, especially vulnerable, underrepresented communities. So that's really our NOAA priorities. And we have this 2030 vision statement of climate-ready nation, a thriving nation whose prosperity, health, security, and continued growth benefit from and depend upon a shared understanding and collective action to reduce the impacts of climate change. So that's really our mission, is to provide that information. The vision for the new blue economy basically says what I said earlier: a sustainable and equitable ocean and coastal economy that optimizes advances in science and technology. That's what Nicole talked about earlier, to create value-added, data-driven economic opportunities. We're very consistent, right, with the UN Decade of Ocean Science for Sustainable Development. So this basically is the objectives and the challenges are listed here and what we want. So of course, the challenges for the decade is to understand and beat marine pollution. That's really important. Protect and restore ecosystems and biodiversity. Sustainably feed the global population, and so on. And this is what we want, right? A clean ocean, a healthy ocean, a resilient ocean, a predicted ocean, a productive ocean, a safe ocean, et cetera. So what we're doing at NOAA is very consistent to the international message, the needs of the international community and and industry and the economy. So what NOAA has done is that it formed a climate council of, led by Dr. Rick Spinrad, the NOAA administrator, and all the AAs, from the different line offices, which I'll show you later. And we have this new group called the Earth System Integration Board, that is basically, so the NOAA Climate Council provides a strategy, overall strategy, even though this document says strategies too. That document is really a strategy implementation plan, what needs to get done. And so we identify these 6 challenges: extreme events and cascading hazards, coastal resilience, the changing ocean, water availability, quality, and risk, effects of space weather, and monitoring and modeling for climate change. And what I'll do is later I'll show examples of what we're doing in coastal resiliency and the changing ocean. Basically, we're defining what we need to do over the next 5 years. And the strategies, all these challenges have a similar climate value chain in which we have to work with the community. We want to work with the community, right? Ultimately, this is what we're serving the community. So we want to make sure we provide the right service, delivery, and decision support tools that the community needs. And that the underpinning of services, right, is the modeling. Make sure we have the modeling right, the R&D right, the data stewardship, and the observations. So you can go this way or that way. I mean, ultimately, everything is underpinned by observations, right? So it goes from, even though it goes 1 to 5 here, one can also think the other way. But it's always really important to not just focus in this direction, but to also look at what the end game is. What type of information is really needed? And then you figure out the rest of it. And this is the NOAA org chart. So what we're doing, we're working across NOAA. So when I showed that previous chart of the strategy, it's not one line office. So these are all the different line offices. So we have Fisheries Service, Ocean Service, NESDIS, which I'm from. OAR does the research. This research across all these line offices, but that's specifically a research organization. There's research within NESDIS, Weather Service, and Office of Marine and Aviation Operations. And so I'm going to now talk about NESDIS. So I'm taking my time, 45 minutes. So I'm going from the big picture to what we do at NESDIS, then focus on the satellites, and then NCI, and then next generation. All right. So at NESDIS, our core mission is provide really the information that's needed by the other parts of NOAA to provide the product and services. But we also generate our own product and services because within NESDIS, which is not just a satellite program, this is where NCI is located, National Center of Environmental Information. So they collect a lot of data from other, from partners throughout the world, as well as within NOAA, to do these assessments, climate assessments and things like that. But within a key part of NESDIS is operating the satellites and providing the products, developing the science that goes into generating the products, and planning next generation of satellites. So I'll show an example of mostly some of the products and the next generation. And we also provide distribution of data. We have a Coast Watch, Ocean Watch node for a lot of the ocean products and coastal products. So I know we have two types of satellites. Is everyone familiar with satellites mostly? Okay, good. All right. So we have the polar orbiting satellites that provides us with global observations, right? So it goes from, orbits South Pole to North Pole. And it's in a low orbit. So as it's orbiting in the same racetrack, for example, the Earth is spinning underneath it, and that's how you get global observations. And that's normally the feed into forecast systems. And then the geostationary, of course, is at a higher altitude, 22,000 miles, and it's moving at the same speed as the Earth is rotating, so it's always overhead. So this is normally used for nowcasting, this is normally used for modeling, but now they're sort of merging together. And you'll see that the next generation becomes more capable, because we're going to actually have an ocean ocean color imager on the next generation. So that's good news. At NOAA, we operate 16 satellites, okay? Our own, plus also DoD, DMSP satellites. But when you look at the international community, it's a lot more, right? And so what we do is we bring in a lot of data from partners. This is a good diagram that shows the different observations that we collect. So we collect our own observations, right? We build our own satellites with NASA. NASA builds the satellites, we operate the satellites. We get observations from partner assets, a lot of data from Europe, for example, from ESA and from EUMETSAT. We're really turning on the spigot for commercial data sources. That's really trending up. And of course, other information, in situ and other data. And that goes into producing data products, information products, and services like, climate assessments is done with an NCI. And these are the services that we feed, right? So we get requirements from the services that says, Weather Ready Nation basically says this is what I need to forecast weather. We have resilient coasts, as you see there, and healthy oceans and climate. So we work with these communities within NOAA, and they work with with stakeholders to figure out what's really needed. And we also work directly with stakeholders. And so we bring all that together and deliver these products. And we're developing systems that are what we call source agnostic. So we're developing the science is enterprise science. So if you have an optical sensor from NOAA or from Europe or from NASA, it doesn't matter. We apply the same science, and we try to have the seamless capability. So this is similar to the other chart, or basically it breaks it down into different sensors. So we have observations from NOAA satellites. We then depend on observations from non-NOAA satellites. Might give us higher spatial resolution from the Sentinels. There's SAR data embedded in here. We don't have SAR data here. There's scatterometer data for ocean surface vector winds. We rely on partners for that. Then there's other partners where we try to get higher temporal refresh and so on. So just the message is that, we work in the community, we work across the communities to get the observations that we need. And there's growing user needs. So we're planning next generation LEO, low Earth orbit, polar orbiting satellites, as well as GEO. So we've identified, climate change is also causing severe weather. So even though we say we have a weather-ready nation, doesn't mean the job's done. We still have to improve forecasts. So there's going to be a trend towards higher and higher resolution for short-term and long-term weather prediction. So we still need more improved measurements in that for those services. The blue economy really needs more information on harmful algal blooms and other ocean biology type of information. And we're looking at hyperspectral ocean color imagery with improved spatial resolution. This is atmospheric chemistry. And on the right with GEO, also we want to, this gives us the ocean complete global view. And the GEO is focusing on the ocean the coastal view, looking at an ocean color sensor, which I'll talk about later. All right. I'm not going to read everything, don't worry. But I want to show you that we're doing all this planning within NOAA. So within that, the previous chart that I showed, the weather, water, climate strategy, which is the implementation sort of part of the high level strategy. This is coastal resilience. Remember, these are one of the challenge areas. So here we talk about the challenges, impact of severe storms, impacts of rising seas, the warming ocean, the loss of sea ice, changing ecology, et cetera, that these are impacting coastal communities. And so we have to provide the information. And so here listed, it was the example, what I talked about earlier, about these are what we've said in the next 5 years, we're going to, deliver, for example, more predictive, more accurate coastal ocean modeling, a suite of products to forecast sea state, marine weather, freshwater ice extent, salinity, water temperature, and so forth. Improve our observational infrastructure, get more data on, bathymetry data and so forth, and water level variability prediction. So there's a lot of, it's sort of a blueprint of what we're doing over the next 5 years. There's more modeling capabilities being developed, for predicting biogeochemical change to sea level rise, warming oceans, things like that. Training, working with communities, better dissemination of information, and developing coastal ocean normals. Changing ocean, same thing, but now it's more open ocean, looking at ocean acidification, affecting marine resources, things like that. And then here is listed better forecast, comprehensive ocean forecast, improve ocean physics, and so forth, more observations, and integrating marine and ice information and so forth. And there's another page of more statistics, computing indicators, being more predictive, and so on. And this feeds into our climate and fisheries initiative that we're working on. This is, of course, no, this is, so we're providing the data that will support this. But the whole idea is that we really want to advance climate and ocean ecosystem understanding. So we're working on that, providing these support systems in order to make them, climate ready decision making. So here's a nice informed. So this curve here, this diagram, basically shows it's time versus sort of resolution, and so this top right here with the clouds is basically traditional weather scales. And so you have the nowcasting of hurricanes, tropical storms, to all the way to what will seasonal forecast and long-term climate projections. And this now we use that sort of concept model for fisheries, real-time industry operations. Then, what should the annual catch limits be? What should rebuilding and protecting areas, and resilience is sustainable. It has different timescales. So we're trying to produce these services, to answer these questions. When is a fishery no longer viable because of a shift in the habitat? When can new fisheries start? How should biological reference points be adjusted for changing baselines, and so on. And so, and we're linking climate to marine ecosystem responses, which is really important because things are shifting. This shows biomass per tow, and you can see 1973 to 2019. It's very different due to mostly ocean heat content rise. And so this is what the system's going to produce, information on tipping points and thresholds, ecosystem-wide forecast projections, species forecast projections, and habitat and distribution maps, going from days to seasons to years and hopefully perhaps decades. So now that's the big picture. Now I'm just going to jump into the satellite part. All right. So there's a lot of information being used that is needed for these services. And so now I'm going to talk about the satellite end of it. So Paul is the chief of the Satellite Oceanography and Climate Division that I mentioned in the introduction, in the beginning. He has 3 branches, and they work on these different activities. So I just want to call them out. They do outstanding science and developing different products and working with the user community and so on. They have up on the upper right is a list of products, but they reach out to the community with information-based products and analysis through Coast Watch, Ocean Watch, Polar Watch, Coral Reef Watch. I have some examples later I'll show. And so there's a lot of information. This is what you get from satellite oceanography. You get temperature, of course, right? You get, we're using more and more synthetic aperture radar that can penetrate clouds and see a lot of good information on sea ice and as well as floods and wind speed too. We have ocean color, altimetry for sea level rise, ocean vector winds using scatterometry, salinity, imagery, and sea ice using also imagery optical systems. So we've been using a lot of SAR data, and this is so NOAA doesn't have its own SAR systems. We rely on partners for the Canadians, RadarSat-2, and the RadarSat constellation to the right, and Sentinel is from ESA, and so it provides a lot of good information. Here's an example of different products and applications listed here. Here's wind speed, so we can get information on coastal wind speed. Impacts a lot of onshore winds, flooding, and things like that. We can look and zoom into areas where there's coastal flooding, shown here. Blue is where there's flooding, and we also get wind speed. This is from a hurricane. And of course, oil spill detection and ice and so on. This is an example of wind speed from Hurricane Ida. So we get that from SAR, and at the same time, we get flooding information. And you can see this is where the where the what is it called? Those where you wall off. What is that? I'm just forgetting. What? Levees. Thank you. I just did it. Yeah, I just did. I couldn't. So you can see where the levees are. Sorry about that. Just had a senior moment. So anyway, so the blue area is where the floods are, and you can see it's holding the water back really nicely. So you can see that from the SAR data. And also SAR, you can actually look at coastal, coastal erosion and things like that. There's a lot of good examples. This is looking at oil spills. So great applications. We have an automated oil spills detection capability using SAR data. Arctic ice, this is ice for a given day. So this is coverage that you get a given day. And you can actually look at ice motion. So that's really important for navigation. See that? Oh, let me go back. Oops, going in the wrong direction. And we're also looking at commercial. So the great thing about SAR, it sees a lot and you see through clouds. The bad thing about SAR is that you don't have it that often, but now the commercial sector is providing higher capability, higher temporal refresh. So we're working with ICEYE. They have a nice constellation of 13 satellites. Soon they'll have 18. And this sort of shows the higher temporal refresh that you get. You can actually track ships. You can use that to track illegal shipping and anything else. So we have a contract with ICEYE to start using the data for oil spills and other environmental responses, illegal fishing and things like that. So that's exciting. SST, we integrate both polar orbiting satellites and geostationary satellites, and we get high temporal resolution SST. We have ocean color from VIIRS and also from other platforms. We use still MODIS, and we use ESA's Sentinel-3 OCLI. And so it really tells us on the biodiversity of the ocean. And That information, of course, is used for harmful algal bloom detection and so on. And we also can generate research products of showing phytoplankton functional types, which is very interesting. As we know, ocean heat content is rising, and this is changing, shifting marine habitats, and we get a good handle on ocean heat content by using information from various sources. So altimetry is one source. Sea level rise, of course, when the sea, when you have clusters where the level is higher, it's usually related to ocean heat content. And then we combine that with sea surface temperature and also Argos floats, in order to come up with good estimate of ocean heat content. But there's a lot of application of altimetry, sea level rise to forecasting hurricane intensity, and so on. And we bring in the other data, right? It's not just satellite data. So here's the Argo program with the profilers and so forth, and the tropical atmosphere ocean array. And so we bring all that data together, and we look at changes in ocean heat content, annually. It's updated periodically, and so forth. Okay, how do we get the data out, right? So we have something. Are you guys familiar with Ocean Watch and Coast Watch? Okay, good. So we have NOAA Coast Watch and Ocean Watch. So they allow us to provide data in tailored data that's tailored into regions and formats, and we make sure the data has quality control, monitored, and provide training and so on. And we get feedback from the community. So we use this as a major portal, and it has a lot of players. There's Polar Watch West Coast, West Coast and Great Lakes and East Coast, and there's Caribbean, Gulf of Mexico, Atlantic Ocean Watch, which is a large footprint. They're also aligned with different line offices within NOAA, and a lot of data providers, external providers, data providers, a lot of users. So we get a lot of good feedback from these programs. The information is valuable, right? We have a 400 million agriculture industry, and it's estimated that because of harmful algal blooms, the cost to that seafood sector is about $20 million a year. So Coast Watch provides that information, additional information. There's also, information from in situ observations, obviously, but we're able to see the areas that are under stress or has these harmful algal bloom issues, and then we can also then use that information to direct more in situ observations to take more detailed measurements. And so we also use information from Coast Watch to be able to respond to emergencies like the Deep Water Horizon oil spill, shown here. And so that's important. Seascape products basically tells us about the biodiversity of marine ecosystems. And that's one of our products that's updated periodically. And so you can actually see how diversity is changing, over decades. And information on sea turtles on long lines. So commercial fishing operations are ceased when longliners accidentally hook and capture and kill endangered turtles. We have information where the sea surface temperature is gradient, looking at these gradients and knowing where the likelihood of sea turtles will be. So that information is used by the fishing industry to be on the lookout for turtles. And then forecasting. So I mentioned earlier that we have to do better in forecasting, and we're moving in that direction. We have these called CHARM, 3-day forecast of these toxins that's using SST and chlorophyll. So that is moving things in the right direction, because you don't want to respond to events as they're happening. You want to prepare for events and be able to predict these events. So that's really important. We have tools, for example, monitoring sargassum algae monitoring. That impacts tourism quite a bit, right? Um, and so on. Let's see. Bathymetry is very interesting from satellites because we can see optically, right? And we can actually see, predict, estimate what the changes look like. So I think the next slide shows Oregon Inlet, North Carolina. This is the change in bathymetry along the coastline shown here. So this is all satellite-based information. So it's very responsive to a current event. We have the NOAA Coral Reef Watch that is based on looking at persistent increases in sea surface temperature. So if you have abnormally warm sea surface temperatures for a long period of time, that's going to be associated with high level alerts. We have really nice websites where you can get that information, and other information is also provided, such as marine heat waves, where they are, and also where they're forecasted. And on the right is a 4-month outlook of coral bleaching. So that information is provided. And also sea level rise. We have a good website on sea level rise and showing, where they're impacting, island nations, things like that. And we're doing interesting science with respect to trying to bring in multi-sensor data. So here's one looking at chlorophyll from VIIRS, looking at sea surface temperature. So there's cold sea surface temperatures, looking at depressed sea level height anomaly due to, cold waters. And so we can show that areas where there'll be regions of, which will have rich nutrients in terms of, so this can help estimate fishing yields and so on. So now I'm turning to NCI. So NCI brings in a lot of data from all different agencies and provides these comprehensive ocean atmospheric and geophysical data, and collects them and does assessments. So they host the largest archives, and they do assessments and things like that. Okay. And the data comes from almost everything, everywhere. So let me just show an example. And what they do, so this is just a schematic that says observations go into analysis for decision making. And they also have a harmful algal bloom observing system. So they have the World Ocean Database and Atlas, which would collect a lot of data, and that could be used for looking at ocean heat content. They have fishery acoustics data set. They have, and this is their data being used to look at the ocean heat content over time. And they have the World Ocean Database that's periodically updated. And I'm just running through this fast. They have this interesting product that they're collecting data from all types of sources on marine microplastic information. So that's something that you might want to look at. Sea winds product, very important for sighting offshore winds. So you can look statistically, where you have persistent high winds, potential use, and so on. I'll skip this one. And also these high resolution climatology focus on temperature and salinity and things like that. Okay, last part. We're almost done. So I'm going to talk about geostationary because that's the one that is more mature in terms of the planning. So we've worked with NASA and NOAA for decades on. NASA usually does the research missions and things that are more mature is operationalized by NOAA, but NASA is still our acquisition agent in making sure they're responsible for meeting NOAA's requirements, and they build the instruments. They have contracts to build the instruments and to launch the satellite, and then we operate the satellite and we generate the products. So this is a series of goes from the very early days to current, and so for decades we've been focusing just on weather, and now we're expanding to other applications, air pollution, and to also ocean applications. So one thing that the feedback that we've got is that, yeah, we can generate nice images of or products of ocean color or harmful algal blooms from polar orbiting data, but a lot of times it's cloudy and we can't use the data. And so the idea is that we know that clouds move during the day and you can composite. And so, and at the same time, we need higher spectral resolution. So we combine the need of higher spectral resolution with the need of higher temporal resolution. And we're going to have an ocean color sensor in geo orbit that should be similar to one, could be similar to the one NASA is developing called Glimmer. So what lessons learned from Glimmer, which will be launched in the later part of this decade, will inform the development of the NOAA operational version in the 2030s. But this is an example of a bad day in the polar world where you have a lot of clouds and it's just that, and this is sea surface temperature and you just don't have that many samples because of clouds. In a week, if you're in an area that's persistently cloudy, in a week, you can get that composite. But here's an example of a day from sea surface, a day from geo, because the clouds are moving during the day and you can peek through the clouds and be able to do compositing. So that's really a concept. And so this is similar to the chart I showed earlier. So we're going from just weather applications from GOES-R to more applications or more capabilities, ocean color and atmospheric composition, and hyperspectral IR too. So these are just a list of applications from what we call the OCX. They're listed here. And again, the challenges overcome by GeoXO will really be the cloud cover and the frequency, and also the spectral resolution to do better job in phytoplankton types and things like that. So that's the motivation for a higher spectral resolution. And this is just a summary of what the instrument's going to do, 300-meter resolution. It says a temporal resolution of 180 minutes, but it's actually going to be better than that. And it's going to be able to zoom in or be tasking. So if you only have some harmful algal bloom issue, let's say in the Gulf of Mexico or nowhere else, you can just say, I'm going to look over the Gulf of Mexico and not worry about the other areas. So we can task it that way. And these are just examples of how ocean data is used in fisheries and sardine habitats. And so I already showed the CHARM hab forecast. Again, I think this is similar to what I showed before on the benefits. And here's my last slide. And so the take-home message is that we are entering the golden age of ocean remote sensing. We have a lot of information from the international community. They're doing a great job making sure the data is open and available, open science, open data. And we're also working hard to reaching out to the users. Ultimately, it's the user community that really drives what is needed in terms of information. The third is we're really doing a great job in the evolution of modeling and data assimilation is really accelerating, especially with high performance computing. So ocean satellite data are becoming more important to improve. Usually a lot of times the weather models are decoupled from a lot of the surface properties, from the ocean. And now we're starting to add that. And that's going to lead to a better weather forecast, but also better ocean forecast. And we see significant improvements. A lot of the agencies satellite agencies across the planet is really stepping up and improving, trending to better satellite sensors for better ocean observations. And with that, thank you.
Thank you so much, Mitch. And always amazed how many satellites you have to work with and partner internationally. Data go to forecasting models, generate the data to the users around the country, around the globe. So I certainly have a lot of questions, but I want to give an opportunity for the audience to ask questions.
Well, I think it's fine.
Oh yeah, they have to do.
Oh, I see.
It's
Yeah.
online streaming.
So, given all the satellites NOAA already has, do you think NOAA is still satellite constrained? For example, could you, instead of 16, could you use 26 satellites or 116 satellites?
Oh,
Is there-
absolutely. Yeah. I mean, we do have limitations. We have budget constraints, right? And so you can
Right.
only do so much.
I guess if you were to wave a magic wand, how much capacity do you think NOAA could still use?
Capacity in terms of
Eyes in the sky.
Oh yeah. Well, you always have the temporal refresh component and the higher spectral resolution. So yeah, we can use a lot more capacity, especially for a lot of the ocean observations. And so yeah, when you compare, when we look at the requirements and compare with what we're actually doing, there's a deficit, there's a gap, and we have to prioritize those gaps. But there are things like, for example, ocean surface vector winds, from scatterometry. We don't have that. So we have observations from Europe in like 9:30 in the morning. And we have observations, there's an OceanSat 3, which is from India, around noon. But then there's really nothing like 2:30, 3:30. So there's a temporal gap. And that's something that, we have a budget constraint, so we can't fulfill all those temporal gaps.
Just to follow up on that, how much do you think surface sensors could help?
I mean, in situ, surface,
yes,
like
bridge that.
Absolutely. I think it's a composite of you want to have sort of autonomous or directed surface observations in areas that are under an extreme condition, right? So if you have a harmful algal blooms and you detect it from satellites will say, oh, there's something there, right? And it will sort of give a relative assessment of the magnitude, but then you want to take more detailed information. So it's going to be a combination of, in situ observations. I would say part of the time it could be directed by satellites, knowing where to collect the information.
That's a good question. One of the slides you show the data buy from commercial satellite. That could be one answer to the question, you over the capacity and then your data buy.
Oh yeah, that's a possibility. That's why we're looking at commercial to see if that will help us out as well.
Any other questions, comments, remarks?
Yeah, as you were discussing how NOAA takes on the operational aspect of the satellite and the receiving the data, does NOAA have its own sea truthing or ground truthing operation, or is that, we've worked with NASA on that in the past, but does NOAA have its own dedicated team for that?
For CalVal?
Yeah.
Yeah, absolutely. And we use, for Ocean Color, we basically fund and man the MOBI out in Hawaii. Okay. So we do that as well. And NOAA has a lot of ground-based observations too. But we also use NASA, observations, Pandora, things like that. That's been set up. Aeronet, for example. And we contribute a little bit too in that. But we have buoys and everything else. But we do, each of that, the set of products that are generated, we have science teams as well as, which includes the CalVal team. First thing, of course, is understanding the quality of the data and looking for these artifacts. But yes. And
is that part of NESDIS? NESDIS?
Yeah. Part of STAR.
Yeah, I remember in addition to CalVal, you also have a team. I remember I visited NESDIS at one time, and they have a quality control team also on top of the CalVal.
Oh, yeah. We have an IC. We have a system that monitors the level 1B, the raw sensor data continuously.
Yeah. Any other questions?
One question from the commercial satellite perspective. Is the current mentality to say, look at the commercial space and see what is available and then say, we'll take this, we'll take that and assimilate together? Or is the mentality, hey, we have this problem, let's work together and build something that can solve this problem.
The mentality so we had an RFI, I guess the input was due end of October, basically to the whole commercial sector, say, tell us what's available. Here are our requirements. Tell us how you can contribute to those requirements. So we did have that call. But then once we have that information, then we have to do an assessment. How will this actually impact our services? Right. So there's there's requirements and there's funding limitations, and then you have to prioritize. So, for example, if you suddenly had a constellation of, let's say SAR, SAR constellation, because I showed that example, we would look at that assessment. We would look at what the commercial vendors can provide. Then we have to work through our services. So we look at the service responsible for, the National Ice Center, for example. We would tell them, this is what, can come from the commercial sector. And they would have to tell us, well, how will that impact the services? So, in terms of efficiency, effectiveness. So if they say, hey, right now, I'm just making up numbers, but let's say they're saying we're 60% effective because we can't monitor sea ice on a daily basis because we just don't get enough data, right? And so going from 60%, we can get up to 90%, let's say, with commercial data. And they would have to basically explain to us what that impact is. And then from there, we would determine the cost, the benefit, cost benefit analysis, right? It's because, I mean, that's always part of the analysis to understand, what is the benefit from acquiring more data. So that's part of our assessment work. Yeah.
Very good. Any other questions?
I just want to real quick. Oh, sorry. Go ahead. Thanks.
I was wondering if you could talk a bit about as more satellites come online and the new satellites have even higher data streams, what's the plan or procedure for you making that data available to people besides, the traditional satellite user of National Weather Service or scientists, things like that? What are the thoughts on that? I wonder if you could talk just a bit about
that. All our data is archived, and it's accessible. So you have data from the archive, but it's accessible within 4 hours, 6 hours. So it all depends. If a user says that, well, I need all this information, but I can live with a delay of 6 hours, then all that data is available. The raw data is available. But then we're also putting more and more data into the cloud, and so people can also access it from the cloud. The big data provider is very interested in a lot of this NOAA satellite data. So, for example, our geostationary data is available in the cloud now, and I think we're moving JPSS up there too. And so that's one way of, providing the data.
Yeah, that's a good question. One of the slides Mitch showed on the ocean data, this Ocean Watch network, they have a regional Ocean Watch centers, and then those center personnel talk to the customers and closer to the users, so they try to understand what they need. Do you need a phone app? Do you need a website? And then how do you get the data in a friendly format delivered the last miles? And then I think there's a lot of effort, different satellite, and then try to deliver that data.
I think it's all levels of service. So, for example, if you're doing weather forecasting, you need data immediately, right? Then that has a higher level of service with backup systems to make sure that data is delivered at 99%. Now, if you're a user that says, I want ocean information, but it could be 6 hours old, then that's easier to deliver that, and that's from the archives. So it all depends.
Yeah, I'm not sure how this is going to be relevant. I'm just curious about some stories, right? Like, have you ever said, wow, due to this technology, this particular thing we have right now, we have actually been able to have this kind of an effect in a real world situation?
Sure.
I mean, any kind of stories like there, you go, wow, I'm so glad we have this technology.
Thinking of Well, I mean, does it have to be ocean stories?
Anything. Just go.
So I know there's a good article in if you look up New York Times, Great Floods of 2019. I think I got the year right. Yeah, 2019. There's a great story how the National Guard used our satellite data to know where the Midwest floods were, and they were able to figure out where to where to rescue people. And FEMA uses our flood products as well, and coastal flooding products as well too. That's always important. Satellite data for ocean applications, ice monitoring is always critical. There was one where we have on VEERS, we have something called the day-night band, and we have imagery at night. And there was I think it's called, I know, it's a crabbing ship called the Kiska Sea. And they were stuck in the ice. They didn't know how to get out of the ice. But they had lights on the ice. And so they called up, I think the Coast Guard, and the Coast Guard called the Weather Service up in Alaska. They were in the Bering Sea. And they were saying, hey, we're not sure. Of course, you know where you are. They didn't know how to get out of the ice. And so the Weather Service looked at the VEERS image, and they said, they basically gave them, go this way, that way, so forth, because they were able to see where the ice was that night. And they knew where the ship was based on the light. But I guess they would have known where the ship is anyway, right, through GPS. But they were able to go through the maze of ice by looking at the imagery. So that's a good story.
20 years ago, there's no measurement of velocity in the coastal ocean. So when someone was lost at sea, got a report, the Coast Guard fly helicopters, they had no idea where the body or the object being drifted, north and south, east and west. Basically, they drop oranges. It's a drifter, we call it oranges. They drop oranges and they say, where drifter goes? Goes to the east and the west, and let track down that way. So that's 20 years ago. In the last decade, NOAA has been funding this coastal radars, and it's basically it's a remote sensing. It's not satellite, but you have this line of sight radar on the coastlines. You send a signal, looking at Doppler return. You can measure the velocity, and that data along the entire California coast now is fully populated, assimilated data every hour into the models, forecasting to the future. The summer report, the Coast Guard pulled the GUI on a helicopter, all the simulated trajectories, and then north of that the circle I'm going to search, and then is that 10 miles, 20 miles, or ellipses, and then orientation of the ellipses, right? So any kilometer of better forecast or translate in the probability of saving lives, and how many ships you need, how many helicopters you need.
Sure.
So it's a huge kind of the story from the data to the platform all the way to the decision making, and then the pilot helicopter access those data real time.
Yeah, I think any major event, like any worst case, you think about a bad event, like if you have an oil spill, how do you know where the oil spill? You get it from satellite data. If you have coastal flooding, you get it from satellite data. If you have, I'm thinking of like, even the coral bleaching, you get that from satellite data, and also the profile data. So there's always a mixture of satellite and in situ data.
Yeah, let's send the speaker. Thanks, Mitch, again.
Well, thank you again. Thanks for inviting me. That's great. Good discussion. Thank you.